Hi guys, welcome to Module 4, Chapter 11, Transformation, Symmetry, and Tilings. I'm Miranda Curtis. Hi guys, hopefully you enjoy this lesson. Okay, question 1. Okay, what type of rigid motion did Ephraim and Devontae use? Okay, we're going to show the rigid motion of the image. Okay, over here is what we're supposed to be solving, but we're going to come into some terminology. Okay, first is a translation. A translation is taking a set of points or coordinated to change to another. So if we had a line right here, we just moved it over. That's a translation. Okay, a dilation is scaling the object down or up. So if we look at our little spots right here, we made it smaller. And if we have a line right there, we've just made it smaller, moved it over. Okay, a reflection is reflecting across a line. If we had a line right here, all it is reflected. Now it is rotated too upside down, but it is reflected. Okay, sorry guys. So over here, our figure, if we look across the line, is just rotation. And rotation is just spinning something around a point. So if we had a point right here and it spin 360 right there, that's where it would go. Okay, it says, what's the rigid motion of the image? Okay, so its rotation, it's 180 degrees. Okay, identify all the lines of symmetry for each below image. Okay, our first image we're going to look at is this diamond, and we see that we can cut across it in the middle. It means we can fold it into 4. Okay, our next one is the triangle, and we can only fold that in half. So that's our line of symmetry. And then our half circle, we can only fold it once. We can fold it in half. Okay, and our rectangle, we can fold it twice. Okay, and then this one, we can fold multiple times on itself. Okay, line of symmetry, but no rotational symmetry. Okay, the triangle means that we can fold it in half, but we can't rotate it. Lines of rotational symmetry, but no reflection symmetry is the half circle and the diamond. And that means we could probably, we couldn't rotate this one all the way, like it couldn't reflect because it's a half. And then this one won't do all the points. Okay, our last one, one line of symmetry and rotational symmetry, not possible with these shapes. Okay, question 3, chapter 11. Myra cut out a rectangular pentagon, hexagon, and octagon, and it seems to her that they form a vertex figure such as the one shown right. Respond to Myra. Okay, so first, we're going to have to look at our shapes. So we're looking at the red one right here, and this is our equation, n minus 2 times 180. It's going to give us a degreeage of the interior angles. It's got 5 sides, so 5 minus 2 times 180 is 540, and then we're going to divide it by 5, which gives us 108. Okay, then we're going to look at our next shape, which is this one down here. It's got 6 sides, so 6 minus 2 times 180 is 720. We'll divide it by 6, it gives us 120. Okay, our next shape has 8 sides, so 8 minus 2 times 180 is 1080. We're going to divide it by 8, gives us 135. And when we add it up, 108 plus 120 plus 135 is 363. Now, the figure does not form a vertex figure only because it equals higher than 360. Now, it's a vertex figure, it's supposed to equal 360, and they overlap. And our shape right here, if you look at it, when you say a vertex figure, it's got faces, and you won't have any out of these. Now, if we took a triangle and we drew it in here, it would give us some faces, and it would equal 360. Okay, question 4. We have demonstrate why triangle QPT equals triangle SPT. Is it true? Okay, we're supposed to do its little line thing. Okay, so we look at Q, P, and T right here to triangle SPT. The relationship is true because PT is congruent to itself, and the S property means side, 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 means all the sides are equal. Okay, demonstrate, it says Q to angles SPT. Is it true? Yes, it's true because the angles are corresponding angles and congruent. So it's going to be the same on this side as it is on that side. That's what that means. Okay, demonstrate Q, P, and we have V right here, this V right here, to SPV. Is it true? Are they equal to each other? And if we look, they are. It says the relationship is true because the PV is congruent to itself, which satisfies the side angle side properties. And we could tell that they are the same. Okay, it says demonstrate why angle QVP is a right angle. Now, if you look over here at QVP, you notice that it's a triangle. So in order for it to be a right angle, it has to equal 180, which we could tell this is. So we know the relationship is true because QVP and angle SVP are adjacent and supplementary angles. So both must measure 90. So when they come to, they have both 90. Okay, question 5A through D. A regular pentagon, PENTA, penta, and an equilateral triangle, angles P, it says P, Q, and R, so this is a triangle, are both inscribings inside the same circle center of O, with P, right there, a common vertex. Demonstrate and calculate of M, of NOQ. Okay, so right here, when we draw it, this little line right here, QRP, we draw that line, that is a triangle. And then if you draw the line from E to N, T to A, then P, and then P to E right here, you are going to get, you'll get a shape that has 5 sides. You have a hexagon. So the center angle of a regular pentagon is 72, and the central angle in an equilateral triangle is 180. So what that's going to give us is our gauge is going to enter, is going, come on, okay. So right here, we looked at N, O, and Q right here is going to give us 24 degrees after we've done our equation up here. Okay, this is fun. Question 6. By holding a ruler, you're holding a ruler to your eye, right here, 2 feet in front of your eyes, illustrating the diagram, Jenny sees that the top and the bottom point of the vertical cliff face, right here, lifted up, mark separates 1.5 inches on the ruler. Jenny is about a quarter mile from the cliff. What is the approximation height of the cliff? Recall that a mile is 5,280 feet. This little guy here is supposed to be Jenny, guys. Just saying. Okay, so first, how we solve this? We have to do the distance from the eye to the ruler is over distance between ruler to marker, and we equals to her distance from the cliff over height of the cliff. Okay, so we have 2 feet over 1.5 inches. Our 2 feet, remember guys, is 1/4 mile, and 1.5 inches is the height of the cliff. And then we have to convert 1 mile equals 5,280 feet, right? So we're 1/4 mile. When we convert, it comes to 1,320 feet. Okay, next we have to put that, we flip it. So we do our equation. So we put the height of the cliff, 1.5 inches, over 1/4 of a mile, which is 2 feet. And then we come over here and we have height of the cliff. Remember, y'all converted things. So you have 0.125 feet over, you have 2 feet, and then over the height of the cliff, remember we converted that 1 mile, and we convert it to 1,220 feet. Okay, now we have to come together and we're going to times 1,320 feet on both sides. So when we do that and we have 0.125 feet times 1,320 feet over 2 feet, the height of the cliff is 165 feet. I know that looks like a whole bunch, but once you follow steps, 1 step at a time, you really do make it easier. Guys, I want to thank you for watching my module 4, chapter 11. This is the end, and thank you guys, and I'll see you next time.